Hello everyone, this is Cambridge O-Level Chemistry paper number 4, alternate to practical. The subject code is 5070. This is May-June 2025 exam. This is the version 2 of this paper. Okay, so let's start. And before we start, we have to remember that in the exam, we'll be given 1 hour to complete this paper. So let's move ahead. So the first question, it says, a student investigates how the solubility of potassium nitrate varies with temperature. The student does these 8 steps. All these 8 steps are written here. So the first step is, it says, put 100 centimeter cube of water into a beaker at room temperature. Then step 2, measures the mass of the beaker of water. Then step 3, adds some potassium nitrate to the water. Step 4, stirs the mixture until potassium nitrate dissolves. Step 5, repeats steps 3 and 4 until a small amount of undissolved solid remains in the beaker. Step 6, measures the mass of the beaker of water and potassium nitrate. Step 7, repeats from step 1 to 6 using water at different temperatures. Step 8, calculate the mass of potassium nitrate dissolved in water at each temperature. Okay, so the first part or the first question we are asked is, the student does not make an important measurement. State the measurement that the student needs to make. So when we see this, one of the things that is missing is the value of temperatures or the temperature measurement that the student has done. So basically, he is missing the temperature measurement. So state the measurement that the student needs to make. So the answer will be temperature. Okay. So temperature, and generally we measure it in degrees centigrade or Celsius. Okay. Moving ahead, part 2, it says the student results are shown in table 1.1. So this is the table we are given. In one part, we are given the temperature, and in the second part, or it would say second column, mass of potassium nitrate dissolved in 100 centimeter cube of water, and the mass is given in grams. So the value of temperature, 15, room temperature, 35, 55, 75, 95. Okay. So good way to do this. First of all, room temperature. Remember, room temperature can be between 20 to 25. A good value over here can be 25. Okay. So we have to estimate the mass of potassium nitrate dissolved in 100 centimeter cube of water at 55 degrees centigrade. So this is the value we have to calculate. Okay. So one way to do is to find out these values or the ratio of these values. So these three values. So here we have delta T, and here we have change in mass. So if we find out this value, so this value is, you can call it as delta M by delta T or immediate slope. So the delta M by delta T, subtract these two, 31.7 minus 26.4 divided by temperature is 10. Okay, this will be your one value. Then you have delta M by delta T. This will be 54.9 minus 31.7 divided again by 10. Calculate this value and do this. Delta M by delta T, 225.3 minus 152.4 divided by, this is 20. Okay. So these are some of the values. So let's try to calculate. I'll open my calculator and to get these values. First value is 81.7 minus 26.4. It is 0.53. The second value is 54.9 minus 31.7. This is 3.32. Okay. Um, and then this value we will create 225.3 minus 152.4 divided by 20. This value comes out to be 3.645. Okay. So any value of slope between these two values will be a good number. Okay. And between these two values, the slope or value which you can take between these two. So let's we take it around 2.5 approximately. Okay, so 2 point if we can say that 2.5 is a good value, or so 2.5 is a good value, so that value will be so if we take delta m by delta t is equal to 2.5, and we our delta t over here is 55 minus 35, this is 20, and this value, let's call it as x minus 54.9. This will be the value, so 20 into 2.5 minus, or rather plus 54.9 will give you the value of x. So remember, this is an estimate, so x, let's try to calculate 20 to 40, so 50 plus 54.9, so this value will be 104.9 x. So let's say our x estimate it to be 1.5 grams. So our x value would be somewhere between this one. Okay. So let's say our mass in grams is 1.5. Okay. So let's start. Next part, it says the student observes that when solution made is so when the solution made at 75 degrees centigrade is left at room temperature, a solid appears in the beaker. Okay. Explain why. So what exactly is student doing? Student is actually heating the mixture, and more as the solution is heated, the solubility is increasing, more potassium nitrate is dissolved in the solution. So as the solution is left at 75 degrees centigrade at room temperature, the temperature will decrease. And as the temperature will decrease, the solubility limit will decrease. And that is the reason why some of the potassium nitrate, which has already been dissolved in the solution, becomes undissolved and will settles down as the solid or precipitates down. So let's write it down. So you can just simply say that the temperature decreases, resulting in decreased solubility of potassium, that's potassium nitrate. Remember, potassium nitrate is KNO3. Resulting in decreased solubility of potassium nitrate in water. Okay, so the temperature decrease resulting in decreased solubility of potassium nitrate in water. This is the reason. So moving ahead, part B says suggest why the student does not do the experiment at 100 degrees centigrade, 115 degrees centigrade, sorry. So remember, the student is making the solution in water, and the water boils at 100 degrees centigrade. So at 115 degrees centigrade, water will actually be in form of steam. It won't be in the liquid form. So just simply says water boils at 100 degrees centigrade. So there will be no solution at 115 degrees C. Okay, this is the reason. Then part C, it says, explain why the method the student uses gives a higher value of solubility than the true value. Okay, so higher value of solubility. The reason is that we are measuring, or there is some inaccuracy when it comes to measurement of mass, and there is a possibility that some of the potassium nitrate remains undissolved. Okay, and that is the reason why the value is giving us higher value than the solubility or the actual value of the solubility of potassium nitrate. So let's write it down. We can simply say that some potassium nitrate remains undissolved in the solution, resulting in higher value of solubility. Okay, that is the reason we can say. So moving ahead, part 2, question number 2, it says a solid W is an impure organic acid, call it H3A. The student determines the mass of H3A in a sample of W by titration with 0.1 mole per decimeter cube of sodium hydroxide NaOH. So the student is doing the following steps. So step number 1, it places the sample of W in a beaker. Step 2, it uses a measuring cylinder to add 100 centimeter cube of distilled water to the beaker. Step 3, stirs the mixture until the solid is fully dissolved. Step 4, labels the mixture X. Step 5, pipettes 25 centimeter cube of sodium hydroxide into a conical flask and add few drops of thiamol ethylene indicator. Step 6, fills the burette with X. Step 7, adds X to the conical flask until the solution just changes color. Step 8, repeats this titration 2 more times. So the first question, part A, it says, explain why it is important to use distilled water, not tap water for the experiment. So remember, distilled water is pure or is a type of water where there are no impurities in it, no minerals, salts, and anything else. Whereas in tap water, there is a high probability that we get some certain contaminations such as salts, minerals, and other aspects. So that is the reason why we use distilled water. So let's write down tap water may contain impurities such as salts, minerals, etc., which can alter the reaction dynamics. Okay, that is the reason why we are not using tap water here. So moving ahead, part B, it shows us initial and final value of burette's reading. So the initial value, let's write it down. VI initial is 4, 1, and remember these are 10 steps, each of 0.1. So 1 and 2, 4.2 centimeter cube. And so since there are no units, let it be 4. And the final value, so the final value is, this is 2 above, so it is 23.8. Okay, so this is our final value. So let's go ahead. So it says table 2 shows some of the students. So table 2, okay. So table 2.1 shows some of the students' results. Complete table 2.1 by writing the initial and final values of titration 1, calculating the volume of X used in each titration, tick the best titration results. Okay. So titration 1, the final value of group Burette was 23.8. Write it down. The initial value was 4.2. Volume used, we just subtract these two. This value will come out to be as 19.6. Then titration 2, 19.1.1. So this comes out to be 19.1, 38.6, 19.3, 3. So it comes out to be 19.3. Okay. So remember, the best results are the ones which are close together in this case. So the close together values are 19.1, 19.3, whereas there is some difference between these values. So the best titration results we can use or tick these two. Okay. So this is how we complete our table. Then in part 2, it says that use the best titration results to calculate the average volume of X used. So the average value, just calculate the average value. Average value, so there are two values. So the average will be 19.1 plus 19.3 divided by 2 comes out to be 19.2. Remember, it's centimeter cube. So answer will be 19.2 centimeter cube. So this will be our average value. So moving ahead, part C, it says calculate the number of moles of sodium hydroxide in 25 centimeter cube of 0.1 mole per decimeter cube of sodium hydroxide. So the concentration is given to us, concentration in mole per decimeter cube. Value is 0.1 mole per decimeter cube. Remember, 1 decimeter cube is equal to 1000 centimeter cube or is equal to 1 liter as well. So here we can say that in 1000 centimeter cube of sodium hydroxide, there are 0.1 moles of NaOH. Okay. Of sodium hydroxide solution, there are. What is the volume? So if we have 1 centimeter cube, the moles will be 0.1 divided by 1000. And if we have 25 centimeter cube of this value, the moles will be this multiplied by 25. Okay. So this value multiplied by 25, it comes out to be 0.0025 moles. Okay. Or we can also write it as in a standard format, 2.5 10 to the power minus 4 moles. Sorry, not 4, it's minus 3. Let's get down. Okay. So my answer will be, you can write any of these values. I'll prefer 2.5 into 10 to the power minus 3. Okay. These are the ones. Then part D, it says the equation for the reaction between H3A and sodium hydroxide is shown. So this is the reaction. Calculate number of moles of H3A that react with 25 centimeter cube of 0.1 mole per decimeter cube of sodium hydroxide. Okay. So remember, we need from the equation, we have 1 mole of acid reacts with 3 moles of base, that is sodium hydroxide. And the number of moles here which are taking part in the reaction are 2.5 into 10 to the power minus 3. These are the number of moles of sodium hydroxide that are available with us in this. So for these number of moles, how many moles of this? So just simply write 3 moles of sodium hydroxide solution requires 1 mole of H3A. So remember, 2.5 into 10 to the power minus 3 moles of sodium hydroxide will need how much? So this will be simple. 1 divided by 3 multiplied by 2.5 into 10 to the power minus 3. These will be the number of moles we need. So this value comes out to be 8.33333 into so on 10 to the power minus 4 moles. So remember, in our exam, we have to go to two significant figures. So the good value will be 8.33 into 10 to the power minus 4 moles. Okay, so this is what we will write here, 8.33 into 10 to the power minus 4 moles. Okay. Then come part E. It says calculate the number of moles of H3A in the sample of W. Remember, this is the sample of W which the student has created. Sample W by titration. Places sample W, measuring cylinder, add 100 centimeter cube of distilled water in a beaker. So this is your beaker, this is your sample. This is your sample, and he adds 100 centimeter cube of water into it. This is actual, so your sample W, let's say the weight is small w, grams, and this small w grams is available in 100 centimeter cube of water. Okay, so we have to remember this. Okay, so the volume of the solution of sample W we have is 100 centimeter cube. So now, so calculate the number of moles. So we have actually calculated the number of moles of H3A that will react with this concentration. Okay, and also remember volume of H3A used, which we have seen earlier, was 19.2 centimeter cube. Moles of H3A used for neutralizing NaOH are 8.33 into 10 to the power minus 4. Okay, and so the number of moles of H3A in 100 centimeter cube of sample W solution. This is what we have to find. Okay, so this value, so the total number of moles used is 8.33 into 10 to the power minus 4. Volume used is 19.2 centimeter cube. Okay, so this will give us the number of moles per centimeter cube. Okay, this will give us number of moles per centimeter cube. And what is the value of solution we have? We have 100 centimeter cube of solution. So we have to find out number of moles. These are the moles that are used for the reaction. So how many were there in the actual solution? So you have to multiply this value by 100 centimeter cube. So just in such case, remember the units should simplify. So say centimeter cube cancel centimeter cube, answer will be in moles. So that is one way to check that you are doing this in a correct fashion. So the answer will be 0.00434 moles. Okay. Or you can call it, write it as 0.434 10 to the power minus 3. No, sorry. Just write. Or two significant figures, we have to write 0.43. Oh. The answer will be 0.0043 moles. Okay, this will be the value of moles of H3A in the sample of W, the one we created in the start. Okay, so moving ahead, it says part F, the relative molecular mass of H3A is 210. Calculate the mass of H3A in the sample of W. So now remember, we have this whole sample. This is our W, and the concentration or the moles we have here is 0.0043 moles. Okay, 0.0043 moles of H3A are here. And what is we have to find the amount in gram or mass in grams of this. So remember the formula that if we have to find concentration in uh, grams per centimeter cube, this will be equal to concentration of a solution in mole per centimeter cube divided by molecular mass. Okay. So what is the concentration of this in mole per centimeter cube? We have calculated that earlier. This is the concentration of this in moles per centimeter cube. The concentration of this in moles per centimeter cube is 0.004, sorry, 0.434 10 to the power minus 4, and dividing it by mole per centimeter cube. Oh, centimeter cube. Oh, sorry. This formula is this mass in grams divided by mR is equal to number of moles. So yes, this is the formula. So the number of moles we can get concentration in grams per centimeter cube of H3A. Let's calculate it. So this value will be concentration in mole. This is 0.434 10 to the power minus 4 divided by, oh sorry, multiply by 2 to the power 10. So this value comes out to be 0.009114 grams per centimeter cube. And how many centimeter cube we have? We have 100 centimeter cube of W. Remember the actual solution that was prepared. So amount in grams will be 0.009114 multiplied by 100. This gives you 0.9114 grams. So two significant figures, 0.91 grams. Okay. So my answer will be 0.91 grams. Okay. This will be my answer. Then part G, it says in step 2, a measuring cylinder is used to add 100 centimeter cube of distilled water to beaker. Explain why using the measuring cylinder makes the volume of distilled water used inaccurate. Suggest an improvement. So remember, generally, measuring cylinder is or does not have fine resolution. Mostly the ones we find in our lab are calibrated to 1 centimeter cube or max 0.5 centimeter cube of resolution. Whereas if you're going to use a burette or a pipette for measuring distilled water and adding it to the potassium nitrate solution, we'll be able to get the resolution up to 0.1 centimeter cube. So it's better to use an equipment that provides you with better resolution. So use a burette or a pipette instead of a beaker. So this right explanation. The beaker generally is a low resolution equipment For example, calibrated up to 0.5 centimeter cube or 1 centimeter cube. Okay. So improvement, it's suggested to use burette or pipette, which are high resolution and can measure easily up to approximately 0.1 centimeter cube. Okay, this will give you better value of measurements and eventually improve the calculations. Okay, so moving ahead, part H, it says that before the student does step 6, the burette is rinsed with distilled water and then with X. Explain why the burette is rinsed with distilled water. So basically, distilled water, when we use to, rinse, basically removes any impurities, and that is why we generally go with it. So basically, to remove uh, impurities and particles inside the burette before experiment. Okay. Part 2, it says suggest and explain the effect of titration results if burette is not rinsed with X after rinsing with distilled water. Okay. So remember, once we rinse it with distilled water, we have to rinse it with X. So when we rinse it with X, there is no water that remains or anything, if any solution that clings to the walls inside the burette, that will be solution X, because that was the solution that was flowed in the last. So if we do not do with X, the last solution that flowed to the burette would be water, and there might be some water that stays or sticks inside the burette. And when we do the titration, that water will mix with our results, eventually degrading the or decreasing the concentration of our solution, which we are using in our burette. And in our case, that solution is X. So if the concentration is decreased, our titration results will be off the charts, or not be accurate. So let's write it down. So the effect will be for effect on titration. So more volume of solution X will be used. Will be used, and titration results or titration results for volume will increase. Okay. The reason is water dilutes the solution X, thereby decreasing its actual concentration. That is the reason. So here we complete our question number 2. So moving ahead, question number 3, it says that a student investigates solid A and aqueous solution B. Solid A is a metal carbonate. Solid B contains only one cation and one anion. The student does not, so student does a flame test on solid A. In question part A, part 1, it asks us to describe how to do a flame test on a solid. Okay, so for a flame test, we can just, if it's very good if we can have the solid in the powder form, or we can just simply uh, use a tip or a wire and put some solid onto it, or roll that wire or tip inside the solid such that some particles of the solid sticks to that wire or that glass rod. Can we use it? And then put that glass rod on burning flame, and then you can have the burning flame using a Bunsen burner and observe the color change of the flame, and and record that observation. That's how we do a flame test. So uh, use a, a glass rod or a wire and roll it in the container having the solid, or use some powdered sample of solid A So glass rod was solid. Now you can use take the glass rod slash wire to the glowing flame. Observe and record the color change of the flame. Okay, that's how you do it. Then part 2, it says student observe blue-green color in the flame. Identify the cation. So cations, remember, they are the positive ions that are there in the salt. So identify the cation present in A. So in your exam, you will be given this table, these tables. So when you're giving these tables, so remember there will be a table for flame test. So remember to see where do we are getting blue green. So we are getting this blue green. It means that the cations are copper to positive ions. So just simply write C from there and use cations are copper to, or you can write Cu2 positive ions. Okay, or Cu2 positive cations. Cations. Okay. Then part B, moving ahead to part B, it says the student adds dilute hydrochloric acid to A. Okay. Then an aqueous solution C and a colorless gas are formed. Okay. Describe the observations the student makes. Describe the chemical test and the positive result used to identify the gas form. Remember that solid A was a metal carbonate. So there is a carbonate, and when carbonates react with hydrochloric acid, they produce carbon dioxide. That will be our gas. So we have what we have identified is that cation is this, and we have the carbonate ions. It's a metal carbonate, so copper carbonate. This is the ion we have, and we are adding HCl to it. So if we add HCl, what we get? We get copper chloride plus CO2 plus H2. So if you have to balance it, we can balance it. CuCl2. We will just simplify this. Yes. Okay. Now this is balanced. So this is the equation of the reaction. So we'll have this precipitate. We'll have this gas, and the another output will be some water. So what the student observation, number one observation will be effervescence, effervescence of of gas of gas is observed. Remember, only carbon dioxide will give you the effervescence. Then the solid dissolves color of the solution. Remember copper chloride. So the color of the solution, let's find out. Cations. So copper solution, if we add, so milky, bluish green. So this will be more of our choice. Carbonate dilute is a test for carbon dioxide effervescence. Okay. So the precipitate will be color of the solution will be changes to bluish green, or you can call it as green. So it's more good to write green, because remember, copper sulfate is blue. Copper sulfate solution, it is generally blue. So it will definitely not be bluish, but it will be bluish green, or good chances that the solution will be green. Bluish green or green. Okay, so we have the two observations here. Effervescence of gas is observed, the solid dissolves, and the color of the solution changes to bluish green or green. Okay. Now the test is pass the gas through lime, this space here, through lime water. We pass carbon dioxide from lime water. Okay, lime result, lime water turns milky, turns milky. And this is also given in your this test for gas. Carbon dioxide, test for gas, turns lime water milky. Okay, pass the gas to lime water and turns lime water. Okay, then it says, explain how the student knows when the reaction has finished. So just simply, the reaction finishes when the effervescence stops. This is a good check to see when the reaction is finished. How the student knows when the reaction is finished? Just simply say, the effervescence stops, indicates the reaction has completed. Okay. Then part C, it says explain how the student uses aqueous ammonia to confirm the metal ion present in C. So remember the aqueous ammonia test. So in aqueous ammonia test, we'll go and see the metal ions. So this is excess sodium hydroxide we are using here, and we are using aqueous for aqueous ammonia or aqueous NH3, you can call it as NH3 aqueous, and NH3 aqueous is also called sodium hydroxide solution. Oh, not sodium hydroxide, it's ammonium hydroxide solution. So we are concerned about these ions. So how to check? Add aqueous ammonia, do precipitate forms, add the you can say add excess sodium hydroxide, excess of aqueous ammonia. The solution, the precipitate dissolves, and the solution gives a dark blue solution. Okay, so this will be our test. And the reason. First of all, add aqueous ammonia to a sample of solution containing C. What we'll observe? Blue precipitate is formed at excess aqueous ammonia. The precipitate dissolves the color of the solution turns dark blue. Okay, this is the test, and you have to just simply write these 4 points. So what are the 4 points? Add excess aqueous ammonia, that's number one. Number two, you have to write the observation of the precipitate, that is part two. Number three, the behavior of the precipitate in excess of the solution. So you write add excess aqueous ammonia, and number four part, you have to write whether what happens to the precipitate, it dissolves, does not dissolve, and the overall color of the solution. So if the precipitate dissolves, the color of the solution turns dark blue. These are the 4 key points you have to mention to get complete credit. So okay. So moving ahead, the part D, it says, this is the last part as well of this question. It says the student does tests on B. The results are shown. Okay. So the test on the sample B has been done. Okay. So the student adds dilute nitric acid and aqueous barium nitrate, colorless solution. Okay. So remember where you add dilute nitric acid and barium nitrate. So dilute nitric acid, yes, silver nitrate, barium nitrate. Okay. So we do this in solution to confirm for sulfate ion. So there is no white precipitate colorless solution. It means that the absence of sulfate ions. There are no sulfate ions are there. Okay. So then, and the second step, another step, nitric acid and aqueous silver nitrate. So nitric acid, silver nitrate. So we do this for these three. So these are actually the group 7 elements, chloride, bromide, iodide. So these three, the test for these three is this. So what happens here? So color of the precipitate, the cream precipitate, it means that chloride is not there, iodide is not there, and only chromium is there. So the chances of having chromium is confirmed. Okay. Then it says add aqueous sodium hydroxide and aluminum foil when warms the mixture. So basically we are looking for nitrate ion. So so for nitrate ions, if we warm, so ammonia gas is produced, which makes popping sound. So ammonia gas is produced, which is a very pungent smell. So we do not see any of such, and the colorless solution forms. So it means that there are no nitrate ions as well. NO3 negative. So only it says identify anion. Anions are Br negative, or bromide ions, or bromide ions are there. Okay, so this is our answer for this question. Okay, so moving ahead to our last part. So the last part is question number 4. It says Q is a mixture of solid copper carbonate and solid lead sulfate. So we have lead sulfate, PbSO4, copper carbonate. Okay, so we have these two and we add them together. So consider it as this is a block of Q. Okay, so this is a block of Q. This is copper sulfate plus, copper carbonate plus lead sulfate. Okay, lead sulfate is insoluble in water. One thing is concerned, does not react with dilute sulfuric acid. Okay, that's fine. Then copper carbonate, again insoluble in water, reacts with dilute sulfuric acid to form copper sulfate solution. Okay, so dilute sulfate, copper sulfate, CuSO4, sulfuric acid, H2SO4. It reacts with these two forms. Plan an investigation to obtain pure copper sulfate crystals. Okay, so remember these are blue crystals. And pure lead sulfate from solid. So we have to basically remove the lead and copper in the form of its crystals. Copper sulfate in the form of crystals and pure lead sulfate form. Okay. So your plan should describe the use of common laboratory apparatus, dilute sulfuric acid, and Q. No other chemicals should be used. Okay. Your plan should include number 1, the apparatus needed. Okay, the preparation of copper sulfate solution. Okay, the method to obtain pure copper to sulfate crystals. Okay, the method to obtain pure lead sulfate salt. Okay, how to test that the lead sulfate is pure. Okay, so wow, purity, you have to check purity as well. Okay, so you may draw a diagram to help answer this question. Okay. So let's start with, first of all, the apparatus needed. So let me make a list on the side. Apparatus needed. Okay. So number 1 would be beaker. You can have a conical flask. You can have test tubes, multiple of them. You can have petri dish, heating, thermometer, temperature measurement. What else? You need filter papers. Okay. You need a Bunsen burner. You need a burner. And you're also checking the purity. So you need equipment for melting point measurements. Okay. Sorry. Melting point environment. So the equipment also contains a big conical flask with paraffin bath. So paraffin bath plus flask. Uh, Thermometer we have mentioned. We also need so glass tube for solid handling. Tube for solid handling. Okay, so so this is some of the things which we can think from back of the mind, and we'll add to this list as we go ahead. Okay, so first of all, let's say preparation of copper sulfate. First part is preparation of copper 2 sulfate solution. Copper sulfate solution. Okay, so first of all with this. So you will make, so this is your part, let's call it as A. So let's call it as A. So this is your sample Q, and you add water into it. And say make 100 centimeter cube or 200 centimeter cube of this sample. Okay, add this, and you also need a stirrer. You can call it, also write a stirrer as well in this. So stir it so that this solution dissolves. Okay. Do we need it? Copper, we are actually using salt. So, okay, so we just extract. So we do not need it. We do not need it. Just make it easier. So we have, this is your beaker. Beaker. This is say your cube, and add H2SO4, sulfuric acid. Okay. So the sulfuric acid reacts with this cube. So first of all, you can just simply write, add sulfuric acid to a beaker containing cube. Okay. What we'll observe, effervescence of gas is observed. Then add excess H2SO4 to the solution. Stir the solution. Add solution. You can say till, just forget about this. So we have to add H2SO4 to the solution while stirring till effer stops. Till effervescence stops. So we have to add it. So once this is done, so we have prepared a solution for that, for copper sulfate solution. So preparation. So this is the copper sulfate solution. So this is this. Okay. Now call it solution A. Okay. Let's call it as solution. This is our solution. Okay. Then number part two, we have to basically so before once we have this copper sulfate solution, what will be happening? So the copper carbonate solution A. So copper carbonate dissolves, whereas lead sulfate remains in the or lead sulfate remains. Okay, it is not dissolved. So see, lead sulfate does not react with dilute sulfuric acid. Lead sulfate remains. So then part is filter the solution A using a filter paper and flask. Okay, so this is your flask. This is another beaker. You pour this solution into here. So you have your filter paper over here, and you'll get your filtrate. So this is copper sulfate solution. Call it as solution B. Okay. So filter the solution A using a filter paper and flask. Okay. So lead sulfate remains on filter paper and copper sulfate solution goes to the beaker. Call it as B. That's it. Okay. So this is, you can say we have now created complete copper sulfate solution and we are calling it as B. Okay. Then part B, so we have now prepared this method to obtain pure copper sulfate crystals. Okay. Part B is copper sulfate crystals. Okay. So I'll change the ink that will. Okay. So I have to prepare the copper sulfate solution. Oh, sorry, crystals. So first of all, heat the solution B till half of the water evaporates. Okay. Then half of the water evaporates. Then you have to leave the solution to cool down at room temperature. Okay. You will get crystals of copper sulfate will form. Okay. You just allow it to cool at room temperature. You'll get really good crystals. So if you do rapid cooling, there will be crystals, but they are not as big. If you want, allow it to, cool at room temperature, and then you'll get good big crystals of copper. Okay, so this is how you can. Then pour the solution on filter paper. Oh no, no, that's fine. And you don't need to dry it because that will, remove the water content as well. So just that's it. That's how you get the crystal first. Okay. Then part it says method to obtain pure lead sulfate solid. Okay. So let's write it as blue lead sulfate solid. So lead sulfate solid. Remember the filtrate. Oh, filtrate of um, solution A on the filter paper is lead sulfate. Dry the filtrate. Dry the filtrate, and you will have your pure lead sulfate. Okay, this is how it goes. Then, what else is remaining? So we have to obtain crystals are done. Method to obtain lead sulfate. Test lead purity of lead. So remember, checking melting point of lead sulfate is you can say a way to check the purity. So purity check. So remember, pour some lead sulfate sample in a glass tube. In a glass tube, you heat the sample in glass tube in a paraffin wax. Measure the temperature when the sample starts boiling. Compare the value of temperature with actual value of melting point of lead sulfate. If the values are same, the lead sulfate is here. Okay. This is how it goes. So if you have to draw the equipment, it's a conical flask that contains paraffin wax that is placed on a stand, and there is a burner beneath it. This is a Bunsen burner. This is sealed from the top, and we have the thermometer. This is your thermometer that is measuring it, and we have the glass rod. Let me draw it. And here the sample will be somewhere here. So this is the glass rod in the sample. Okay. So this is your paraffin wax. This is your thermometer. This is your glass rod. This is your burner. This is your stand. Okay. So for purity check, you need to have this melting point measurement setup. And this is a conventional way to measure the melting point of any solid or solid in its powdered form. And you just heat that solid in the presence of high melting point liquid. And in this case, we have paraffin wax. We have a temperature as well over there. So when we just observe the material, and when it starts boiling, we measure the temperature and then compare our recorded readings with the value we have in the data sheets available to us in lab. And if the temperature aligns, it means that we have a pure substance in front of us. Okay, so this is how this last part is done. So how the let's say. So one thing we need to ensure that leave some space for apparatus needed, and for apparatus needed, you can in the end you can also write that for all these aspects, some of the things we need. Beaker, yes. Conical flask, we use test tube. We haven't used it, so we can remove this as well. Petri dish, yes, you can say it. Dry the filtrate, lead sulfate, dry the filtrate in Petri dish. You can dry this in Petri dish. So we use a thermometer, we use filter paper burner, and then we have this melting point equipment, yes, and we have the sterilizer. So yes, so these are some of the equipment we have used, and this is a list of it. Okay, so this is how we end up solving this question, and I hope you have learned something from this video. And if you have learned something, if you want me to explain other papers or other concepts as well, please let me know in the message. And wish you best of luck for your exams. And stay tuned and share this video with the friends and who are interested in and who want to learn and want to prepare for their exams as well. Thank you very much, and stay tuned for the next video.